Hi, thanks for joining me in this tutorial on effective data visualization. My name is Husni Almoubayyed. I'm a PhD candidate at Carnegie Mellon University working in cosmology. While most of my work involves programming in Python, data visualization has become something I'm particularly passionate about, so I'm really excited to have this opportunity to present this tutorial. Throughout this tutorial, I will assume that you are familiar with standard Python syntax, as well as with basic Python programming and basic plotting in Python or some other similar language. After this tutorial, you can expect to have expanded your knowledge of what's possible when it comes to visualization in Python, and to have some practical experience visualizing different types of data in different industries. You can also expect to build essential skills in visualizing high-dimensional data, studying data through statistical visualization, creating interactive charts, and confidently designing plots that effectively communicate your results. So before we get started, just a quick introduction to some of the packages and datasets we're going to use throughout this tutorial. So matplotlib is the main plotting package in Python. It can do a lot of things and has a very wide scope, but it can be a little difficult to deal with sometimes. Seaborn was built on top of matplotlib to make it easier to do statistical plotting. Pandas stands for panel data, and it is a useful library to handle things like tabular data or time series data. NumPy is one of the largest Python libraries and can help us do almost anything we can think of to numerical data. And then sklearn is a widely used machine learning library with a simple, easy-to-use API. So next, let's look at some of the data sets. The first 6 listed here are going to be easily imported from seaborn or sklearn, and these are a data set on diamonds, a data set on flights in the 50s showing numbers of passengers per month, a data set on the properties of iris flowers split by 3 species, and scomb, which is a data set made up of 4 different data sets that all have the same mean and standard deviation, but they all look dramatically different. And finally, a data set of hundreds and digits. We will also use stock market financial data, which we'll be requesting in real time from Yahoo Finance using pandas, as we'll see later on. And then finally, a data set of confirmed COVID-19 cases by county in the US. So to install the packages that we'll be using, you can run this cell and it will install all the packages for you. This is assuming you have pip and Jupyter installed. If you don't, pip installation instructions are available here at this link, and then you can run pip install notebook to install Jupyter. An alternative would be to install an Anaconda distribution, which would come with pip and Jupyter. And then if you're having some issues with this and you would rather not worry about installing packages on your own, you could go to this bit.ly link. This is going to be a link to a Google Colab hosted version of this notebook, which could run in the cloud and you wouldn't have to worry about installing your own packages on your own computer. And finally, I like to put these few imports at the top of every notebook that I open. So I'll explain them here. So the first one is going to import both NumPy and matplotlib. The second cell here is going to first import seaborn, set its style to a dark grid. These settings are going to affect every plot that we make with seaborn or matplotlib. It's going to set its context to a notebook and increase its font size by 50%. And then finally, it's going to set the colors that we use to a colorblind friendly set of colors. And then finally, this third cell, the first command here is going to change the back end of matplotlib into a higher resolution option. So on my Mac OS, it's going to set it to a Retina, and then This final command is basically going to change the figures of every plot we make to make it a little bit bigger than the standard for matplotlib. All right, so now we're ready to get started. So this tutorial is segmented in 5 chapters, and these 5 chapters are essentially the main reasons why people visualize datasets in the first place. 1 is data exploration, 2 is density estimation, or essentially knowing more about the process that is generating your data. 3 is visualizing high-dimensional datasets via dimensionality reduction. 4 is interacting with the data, and finally 5 is communicating through plotting. So certainly one of the main reasons people visualize data in the first place is to explore data sets. Certainly anytime I look at a new data set, the first thing I do is I plot it out to see how it looks like. So this is going to be our first topic for today, data exploration. So we're going to start by looking at the Anscombe data set. This data set is made up of 4 different data sets, and each one of those have the same first 2 moments, but they look completely different, and this is what we're gonna see today. So we first start out by loading Anscombe from seaborn, and then what I'm doing here is that I'm asking seaborn to describe for me each one of those data sets. And what describe for seaborn means that it returns some simple statistics on that data set. And let's see how this looks like. All right, so as you can see, for each of those data sets, we have 11 data points, and then the mean, standard deviation, and all the basic statistics are basically the same. Not necessarily the quartiles, but the first 2 moments, the mean and standard deviation, certainly are the same. So really the simplest thing we could do here is a scatter plot, since each of those Anscombe data sets are just 2 dimensionals, have x and y. So let's see if we can plot the x and y coordinates of the first data set on a scatter plot. So we're gonna tell seaborn that the x is the one labeled x, the y is the one labeled y, and then the data is gonna come from Anscombe, but we only want the data that matches data set being the first data set. And let's see how this looks like when we plot it out. All right, so 11 data points, kind of increasing in x and y. So looking at this, it kind of looks like it correlates positively between x and y. So one of the first things we might try and do is to fit it to a linear regression model. And we can simply do that using a linear regression model plot, or LM plot. And some plots in seaborn don't follow the matplotlib figure sizing settings. And for those, we can just add a height parameter. And let's just add a height of 8. So this is how it looks like fitted to a linear regression model. And then the shaded area is the standard deviation of this fit. So this worked for the first data set. Why don't we just try to also fit the second data set to a linear regression model? Right, so the second data set obviously is very different from the first data set, and a linear model is not going to work. It kind of actually looks quadratic. And seaborn allows us to do a quadratic fit very easily by just using the order argument. So if we just use a second order linear regression model fit, we see that this actually fits it perfectly. One thing that's interesting to note is that the first and the second data set, even though one is kind of linear and the second is actually perfectly quadratic, they have the same mean, the same standard deviation, which is why plotting is important, because it would have been really difficult to know that these two data sets actually look really different without plotting them just by looking at the statistics. And so let's do this again for the third data set. All right, so this data set is obviously linear with one outlier. So let's actually go back to an order of one, which is the default, so we don't have to actually type it in. And let's see how that looks like. All right, so this kind of works, but it's very heavily influenced by this outlier, which is normal for a linear regression model fitted by a least squares error metric, which is what's going on here. So what if we want some fit that is not heavily affected by outliers? We can use the robust argument here and set that to true, and this is gonna give us a robust fit. And I'm also gonna just set the confidence interval to none, because otherwise it might take too much time to calculate the confidence interval. So let's see how that looks like. Right, so perfect. It ignored the outlier, which is what we really wanted it to do at this point, and fit a linear regression model to the linear data. All right, so now let's look at a different data set. This is going to be the iris data set, which we can load it up in exactly the same way as we loaded up the Anscombe data set by just saying iris instead of Anscombe. All right, so loading it up, and then let's see how it looks like. And we can do this by saying iris.head, and this is going to show us the first 5 rows of the iris data set. Iris here is a pandas data frame, and this is the common syntax for a pandas data frame. All right, so this is how it looks like. There's 4 dimensions here that are the sepal length, sepal width, petal length, and petal width. And there are 3 species. It's not apparent here, but there are 3 total species of iris flowers represented. And let's say we want to make a scatter plot of the petal width and petal length. So let's do sns.scatterplot, and then the x is going to be the petal length, and the y is going to be the petal width. One really useful argument here is hue, and this is going to color them with different colors in accordance to a third dimension. And in this case, we're going to use the species to color them 3 different colors for the 3 different species represented. And then we're going to say that the data should come from the iris data set. And let's see how this looks like. All right, so we were able to plot the petal length versus the petal width for the 3 different species in 3 different colors. Now, as an exercise, try to fit 3 linear models to the 3 different species here as we've done above, but try fitting the 3 different models on the same plot. All right, so we can again use Seaborn's LM plot, and basically we can go ahead and copy these arguments over. And let's just add a high parameter of 8 and see how this looks like. Right, and this is pretty much all you need to solve this exercise. Now, a scatter plot can be helpful, but what if you want to know a little more information about the
Marginal.
distributions of the x and y axes as well as a scatter plot? For that, we can use Seaborn's joint plot. And again, let's copy these parameters over with the exception of hue and see how this looks like. All right, so now we have a histogram of both the petal length and the petal width as well as the scatter plot. And we don't have to stick with histograms. Actually, the second part of this tutorial is going to talk about histograms more, but it's also going to talk about kernel density estimation. And you can use kernel density estimation in a joint plot by just specifying the kind of the joint plot as KDE. And this is going to give us something that looks a little better to try and estimate the x and y and joint distributions. All right, so this is pretty useful, but do we really have to do this for every 2 dimensions of our 4-dimensional data set? What if we have something even more? Do we have to repeat this process? And Seaborn actually has a pretty useful plotting function called pair plot, which is going to plot each 2-dimensional pairs together as a joint plot and return that. So for here, we just want to give it the iris data set in general, just specify the height, and let's also add hue to color each species as a different color. So here we're going to say species. And let's see how this looks like. Might take a while since it's plotting a lot of different plots at the same time now. All right, so we have 4x4 plots showing each 2-dimension against each other dimension. And on the diagonal, it's just those distributions of that dimension. So for example, this is the sepal length distribution. And then, for example, this one here is the petal width versus the petal length, and so on. So this could be pretty useful in looking at all of the pairs of dimensions plotted against each other. We should also note that this is symmetric. So this plot is the same as this plot with the exception that this one has petal width on the y and petal length on the x, whereas this one has petal width on the x and petal length on the y. All right, so we talked a lot about plotting numerical data now, but what about categorical data? For this, Seaborn also gives us a simple plotting function called catplot for categorical plot. And here, let's say we want something numerical on the y-axis, so something like the petal width, and then something categorical on the x-axis, such as species, which we know there's only 3 of them. And we have to specify what kinds of categorical plots we want. So let's just say we want a point categorical plot. So just a point and a standard deviation. And then the data is going to come from the iris data set. Now let's see how this looks like. All right, so pretty much as expected, we have points at the centers of the petal width for each of the 3 different species, and then we have a small stick corresponding to the standard deviation. Let's specify a height parameter to make this a little bit bigger and more clear. All right, so it looks something like this. A point categorical plot is not very informative. Something that is much more informative is called a violin plot, and this is going to show us the distribution of the petal widths for each of those 3 species on the same plot. So we can see that the setosas are a lot more concentrated around the quarter, whereas virginica are more widely distributed between 1.2 maybe and 2.7. All right, let's do some exercises now. So we have 3 exercises here. The first one is saying, let's load up the flights data set and then plot a linear model of the passengers number as a function of year, and then separating those by month. So plotting each month in a different color and the linear model for each month. The second exercise is load up the diamonds data set and then plot the price of diamonds as a function of carat with different color grades in different colors. And there's a lot of data points in that data set, so do play around with the plotting characteristics. Here I'm giving some advice. Try and figure out how to change the marker size, change the transparency or alpha to something like a half or less, and then try to add some jitter to the X values, because otherwise a lot of diamonds are going to have the same X values, the same carats, so it's not going to be very clear. So there's going to be a lot of points on top of each other and it's not going to be very clear. And then finally, the third exercise is saying load up the Titanic data set, again from Seaborn, and then make a box plot using categorical cat plot of the fare of the ticket paid for different passengers on the Titanic on the y-axis, and then the 2 different classes of whether someone has survived or someone has not survived on the x-axis. All right, so let's look at the solutions of these exercises. So the first one, loading up the flights data set, let's load it up just how we did with IRIS and ANSCOM, and then look at the first 5 rows, see how it looks like. So it has 3 columns, year, month, and passengers, and we want to plot the year on the x-axis, the y, the number of passengers as a function of year, and then hue is month, and this is going to color each month separately and also fit each month separately. And then we have a fit regression here to false. If we run that, it's not going to show the linear fit, so let's remove that. But if you want an LM plot without the linear fit, that would be the way to skip this regression fit. And let's run that and see what we get. All right, so these actually do look pretty linear. So we have a linear regression fit to the number of passengers as a function of year for different months of the year. All right, the second exercise was loading up the diamonds data set, and let's look at how this looks. And now we want to plot the price as a function of carat with different colors, colored differently. And then let's have a pretty large size for this plot since there's a lot of data points. And then we're using a marker as a dot. And then we're adding some jitter in the x direction, and this is going to add some random noise in the x direction, just so things don't all line up on top of each other. And then here, scatter keywords is we're basically telling Seaborn to pass on this argument to the base function in matplotlib. And we're asking it to pass in an alpha of 0.3, which is going to make data points more transparent. And then here we're restricting our plot to carats between 0 and 4 and to prices between $200 and $20,000. And running this, we get a plot that looks like this. All right, so we can see that, for example, green colored things are cheaper than pink colored things. And if we look here, we see that green is J, whereas pink is D. D actually corresponds to very colorless diamonds, whereas J corresponds to a little bit yellowish diamonds. So this really makes sense. All right, and then the last data set we have is going to be the Titanic. So let's load it up, see how it looks like. And we basically have a lot of information about Titanic passengers, whether they survived, and then different information about them. But we only want to look at whether they survived on the x-axis. So we're using a cat plot here, just as we did with the violin and point plots. But here we're using box for kind, which is what we want, a box plot. And we want the fare paid on the y-axis and whether they survived or not on the x-axis. And let's see how this looks like. So now we can see some information regarding this, and some observations could be that the average price paid for passengers who survived was higher than the one paid for the ones who did not survive. Obviously, there's a lot more dimensions to this problem, and this may or may not be a good predictor of survivorship, but it is always important to visualize different things together in a data set, as we've seen. And finally, let's talk about data that is not suitable to project it on x and y coordinates. And one example of this could be angular data, where we need something like polar coordinates to project it on, or map data, where we need something like a mile-wide projection to project it on. And before we do this, let's first get familiar with quiver plots. So quiver plots are plots that are basically plots of arrows. So we're not just plotting data points, but we're also plotting data that has positions, but also it has direction. And we can pull up the help on quiver by doing plt.quiver with 2 question marks, and we get something like this, which says that quiver can take x and y, defining the arrow locations, but also u and v, defining the arrow directions in the x and y direction. So let's see what this means. Let's say we want x is uniformly distributed between 0 and 10, y is uniformly distributed between 0 and 1, and then u is just ones and v is just ones. And finally, we're going to use matplotlib subplots and add a quiver plot on it. These head length and head axis length are basically hiding the arrow, and we're going to use that later, but let's take them out and see how this looks like just as is. All right, so because u and v were the same, then this is going to point at 45 degrees between the x and y axis. If we add those 2 arguments back, then the arrow is just not going to appear. And now let's say we want to use polar coordinates instead of x and y coordinates. We can simply do that by adding the polar equals true argument to the add subplot. But this is going to get a lot more complicated than that, because the x and y here are no longer x and y. They're actually theta, the angle, and r, the radius, which are the 2 polar coordinates in 2 dimensions. So now let's say that our angles is going to span from 0 to 2 pi, so all 360 degrees, and our radius is going to go from 0 to 1. And these are the equations to do the change of coordinates from x and y to r and theta. So now u is going to be the cosine of theta, and then v is going to be the sine of theta. These terms are 0, but I left them here for completeness. So let's see how this looks like now. All right, so we got a spiral here, and the reason we got this is basically we're going uniformly in radius from 0 to 1, which is what's happening here, we're going uniformly in radius in the position of the in the position of those sticks from 0 to 1, but also the angle is changing from 0 to 2 pi. So it's going in 360 degrees. So now, what if, say, we want all of those sticks to be uniformly distributed across this circle, but also to be all pointing towards the center? Now you can notice that all of these sticks are already pointing towards the center, so the only change we need to do is that instead of having the radius being linearly spaced from 0 to 1, let's just have it as randomly sampled from a uniform distribution between 0 and 1, and see how this looks like. All right, so using that, we got radial sticks. A few exercises now is try to do this radial plot again, but make all the sticks start from a radius of 1. And exercise 2 is try to have all of those sticks horizontal. So when I say horizontal, I mean horizontal, all pointing to the left or right, as if this was an x dimension. And then the third exercise is try to use a mul-wide projection. You can do this using the argument projection in the add subplot, and also keep all the sticks horizontal, but make sure that the sticks span the entire space. All right, so let's first copy this code over here and do the first exercise. So the first exercise is asking us to do the same, but now all of the sticks are going to start at a radius of 1. So we can just change this r to 1 and run this again. And this is pretty much what we wanted. Now the second exercise is asking us to make all the sticks horizontal. So let's first change that back. And now to do that, we're just going to set u to 1 and v to 0. And the reason that works is that, remember that u is what controls the x direction and v is what controls the y direction. And then finally, we want to use a mul-wide projection. So instead of this polar equals true, let's say projection equals mul-wide. And let's see how this looks like. So this kind of works, but all the data points are in this quarter. So what can we do about this? So we notice that our theta is going from 0 and forward, but here we have angles back to minus 180. So a way to fix this is to change this 0 to minus pi. We really don't need this 2 anymore. And then this radius is going from 0 to 1, but really it should be going from minus 1 to 1, since we want to go to the bottom half as well. So let's say minus 1 to 1 and see how this works out. So this is all we have for data exploration. Part 2 is going to be on density estimation. All right, so let's move on now to talk about density estimation. So in many cases, you plot things to try and estimate the distribution that generated your data. And we're going to be talking more specifically about nonparametric density estimation, and we're going to talk about a few ways of how to do nonparametric density estimation. And the simplest way to really do that is by taking the histogram of your data. So we're going to start with that first. Let's use the iris dataset for now, which as a reminder looks like this. And specifically, let's look into the sepal length for now. And so as I mentioned, the simplest thing we could do is just to take the histogram of the data, and we can do that using matplotlib very easily. And we get something like this. It's important to note that the number of bins really make a difference when it comes to histograms. So let's do that again using subplots in matplotlib to plot two histograms next to each other, one with only 5 bins and one with 500 bins. And let's see how that looks like. So I'm going to plot a histogram here of our data, and then just say 5 bins. And then I'm also going to normalize the histogram by setting density to true. And then I'm going to do the same thing here, but now bins is going to be 500. And again, density is going to be true. And let's see how that looks like. So maybe 500 was too many to visualize. Let's just do 100 for now. All right, so as you can see, these two histograms look very different from each other. And let's actually look a little more into what histograms mean. So this histogram, for example, is saying that around 10% of the sepal lengths fall in between something like 7.1 and 7.9, while around 38% of the sepal lengths fall between something like 5.8 and 6.5. Whereas we can see a lot of variations in the sepal lengths distribution on the right-hand side. So let's look more into the number of histograms and how that affects the accuracy of the density estimation. So essentially, there's going to be a bias versus variance trade-off. And the way I like to think about this is that if you have a histogram like this and you add a data point to it, it's not going to look much different. In the extreme example of just having one bin, for example, wherever we add the sepal length, it's not going to make any difference to the histogram. Whereas for the histogram on the right-hand side, if we add one sample somewhere, then it will make a difference to this histogram. So what this means is that the histogram on the left has low variance, whereas the histogram on the right has high variance. But then there's also bias that we have to look into. So the histogram on the left does not really match any data point. So it does not really match the true shape of the data. It's highly biased. Whereas the histogram on the right has very low bias because it's specifying the density exactly at each data point. So it has basically zero bias, but very high variance, whereas the histogram on the left has very high bias, but very low variance. And if we do the math, then we get that the expected value of this error, which is the sum of the variance and the squared bias, is going to scale inversely with the number of data points, which makes sense. If you have more data points, then your histograms are going to be more accurate. But it's going to scale to the power of minus 2/3, which is a slow scaling with the number of data points. So this begs the question that, can we do better? And the answer is yes, we can do a little better with kernel density estimation. So with kernel density estimation, instead of just plotting histograms, we're going to turn each data point into a kernel. And a kernel is something like a Gaussian or a box or something like that. And it really has to satisfy a few conditions, which is that it's positive definite, and that it is symmetric around its center, and then that it sums up to 1, which means that we can use it as a probability distribution. So let's look at what a kernel density estimator looks like for our current data set. And we can do that using seaborn dot KDE plot. And then let's pass in our data and see how it looks like. So this probably looks a little better than what we had up here. And it probably works better as a way to predict the distribution that generated the data. But again, we have the similar issue of choosing the width of the kernel. So for example, choosing the standard deviation of the Gaussian in the case of a Gaussian kernel. And using seaborn, we can specify the bandwidth of the kernel. You can always try different things to see what looks more reasonable as an estimator of the true density. But then we still have the same bias variance trade-off. And really the only difference is that the expected error from a kernel density estimator, given that we've chosen a reasonable bandwidth, is smaller than the expected error of the histogram. And unfortunately, we really cannot do any better than a kernel density estimator, because it is the estimator that provides us with a minimax error. So now as an exercise, try doing a kernel density estimation, try plotting a KDE plot with 2 dimensions now, so with both the petal length and the petal width. And let's just see how those look like on a scatter plot first. And so this exercise can also be simply solved using seaborn, using a seaborn KDE plot, just like we did before, but now passing the new data, which is going to look something like this. And what this is telling us is that the points here and here are the peak in the joint densities of the petal length and the petal width. So one last thing, a really nice seaborn function is the dist plot. And what this basically does, let's just do the dist plot of the distribution of petal lengths. And what this really does is that it does a histogram, and overlaid on top of it is a KDE plot. So you immediately get both plotted on the same plot. All right, so let's talk about visualizing high-dimensional data sets and reducing the dimensionality of high-dimensional data sets. So for this part, we're going to need these imports, and I'm going to talk about them as they come up, but let's import them first. So one of them is this load digits import, and we're basically loading up a data set of handwritten digits. And you can treat this data set as basically a dictionary. So using the key images and the key data, let's see what we get. So we get an 8x8 image, so 8x8 pixels per image, and then there are 1,797 samples. And then this data is basically these images unfolded. So 8x8 is 64, and then we have 64 pixels and 1,797 samples. So first, to get familiar with the data set, let's just plot one of those images, how it looks like. So we can use matplotlib's imshaw function for this. Let's get the first image plotted and see how it looks like. So as you can see, it's a handwritten 0. And then you can look at other images just to get familiar with them. And this is a 5, apparently. This is a 3, and so on. And then the question is really, do we need 64 different dimensions just to encode the fact that this is an image of 3? Can we use less than 64 dimensions? And we're going to talk about two different ways that we can reduce the dimensionality of data sets. And so the first one is going to be the principal component analysis, or PCA. And PCA, what it basically does is that it projects the data points on axes that maximize the variance. So to understand what this means, let's use some very simple data set. Let's create one where, let's say, it's two-dimensional and the x-axis is just a linearly spaced set of points between 0 and 9. And let's say there's 10 of them from 0 to 9, and then y is also the same. So from 0 to 9, 10 points. And then if we plot this using a scatter plot, then it's going to look like this. So 10 points along the diagonal from 0 to 9 in both x and y. So the question again is, do you really need two dimensions to understand all of these points? Can we just use one dimension? And so these points can really be just projected on this diagonal axis and just explained by that diagonal axis. So let's try to use scikit-learn's PCA class to see what we get from reducing the dimensionality of this two-dimensional data set to one dimension. So for this, I'm going to use scikit-learn's PCA, which we've imported it earlier from scikit-learn.decomposition. And just like any other scikit-learn class, the way to use this is first by initializing it, and then we're gonna use one component, meaning we want to reduce this to one dimension. And then we're gonna fit this PCA by doing PCA.fitTransform, and then giving it our data set, which is gonna be a NumPy array of x and y, and then we're just gonna transpose this to look in the basically in the format that scikit-learn accepts. And just to show you what this looks like, this should look like this. And then if we run this and get the components, then we should be able to plot the components. Also, just to confirm, the components should be 10 data points. And then to plot this, let's just use matplotlib's scatter plot. And then we're going to plot the components on the x-axis and just the zeros on the y-axis and see how this looks like. So as expected, we basically projected these data points onto the diagonal axis. And just to confirm, the distances between each two data points here is square root of 2, which is the distance, the diagonal distance between each two data points here as well. So we got what we expected, and we were able to reduce the dimensionality of this data set from 2 to 1. To learn more about PCA, like a little beyond the scope of this tutorial, you can check out these resources to either get some cool visualizations out of PCA to understand it a bit more, or to learn more about the math from the second resource. And now it's time for an exercise. So just like I used PCA now to reduce the dimensionality of this fake data set from 2 to 1, try to use it to reduce the dimensionality of the digits data set from 64 to 2. All right, welcome back. So to solve this, let's do pretty much what we just did with the fake data set. So initialize a PCA class with two components, and then our components are going to be, again, a fit transform Now we're going to use the digits data. And then we're going to, again, use a matplotlib scatter plot to plot the components. So the x components are going to, we can extract them. So the first column of every row, and then the y components. And then basically to get the color coding of different classes, we're going to use C for color, and then this is going to be the target digits. So this is basically, it tells you that, oh, this image is actually of a 0, or this image is actually of a 1. And then since there's going to be a lot of them, let's reduce the visibility of each to half. And you can play around with this if you like. And then we're going to talk about colors later, but let's just use a color map. So let's get a color map from matplotlib. Here I'm asking matplotlib to give me a color map of the paired colors, and I want 10 of them. And we're going to talk about colors later in the communication section of this tutorial. So let's see how this looks like. All right, so let's just add a color bar to this to know basically which data points are which digit. All right, so here we were able to kind of separate some data points to, like, for example, the majority of the zeros are here, the majority of the ones are here, the majority of the fours are here, and so on. So we were kind of able to separate them and encode a lot of information in just 2 dimensions rather than 64. All right, so let's talk now about the failures of PCA and basically in what situations does it fail. So generally, PCA is going to fail if you have a nonlinear data set, since it's a linear method. And one of the classic nonlinear data sets is a 3-dimensional Swiss roll. So let's try to use PCA to reduce the dimensionality of a 3-dimensional Swiss roll into 2 dimensions. So here we're just going to make a Swiss roll using scikit-learn's make Swiss roll routine that we've imported earlier. And then let's actually cluster this Swiss roll into 5 clusters using scikit-learn again. And this is basically going to help us visualize it a little more easily, and then we can basically know whether our PCA is successful or not. So it would be successful if the Swiss roll basically unfolded and that we saw distinct strips of different colored clusters. And let's see if that happens. And you don't really need to pay too much attention here, since clustering is in particular beyond the scope of this tutorial. So we'll go ahead and make the clusters here. And then we're going to use matplotlib's 3D plotting package to basically plot this 3-dimensional Swiss roll on 3 dimensions. And we're going to do that by first initializing a figure object, and then we're going to ask matplotlib to make this figure into a 3-dimensional one. Here we're just basically deciding on which angle we want to basically view this figure from. And since we're basically viewing a 3-dimensional thing on a 2-dimensional screen, and you can play around with this and see how it affects the figure. But I found that this angle works pretty well for this particular Swiss roll. And then, so a trick is that if you want matplotlib or seaborn or something to basically plot different data sets in different colors, you can just iteratively plot those data sets. So here we're iteratively plotting the data points that match a specific label, and these labels are basically one of those clusters. And then we're saying we want the X component, and then the Y component, and then the Z component. And then if we run that, we get the Swiss roll. And now let's see if we can actually reduce the dimensionality of the Swiss roll to 2 dimensions using principal component analysis. So just like what we did before, we'll use a two-component PCA, and then we're gonna fit this to the X data points, and again, the X data points are the ones that were created from the Swiss roll. And then let's plot out the X and Y components, again, for each cluster using a seaborn scatter plot. And as you can see, this wasn't really as useful. So a lot of points seem similar. All the orange points here and the red points seem similar to PCA, whereas in fact they're very distinct. So the red ones are out here, and then the orange ones are in here. And one of the really cutting edge ways to do this dimensionality reduction is that can deal with non-linear data sets is t-distributed stochastic neighbor embedding, or TISNE. So without getting too much in the details, we can say that TISNE tries to construct a low-dimensional embedding with the minimum difference to the high-dimensional data set, where difference is calculated according to a probability distribution that keeps similar data points together. Another way of looking at this is that TISNE tries to preserve the local but not necessarily global structure of a data set in a lower dimensional space. And for more information on TISNE, you can view this original paper. And the way TISNE is implemented in scikit-learn is actually very similar to PCA. So let's first import TISNE, and then here we're initializing a TISNE object and then fitting it to the Swiss roll data points. One thing to note here is that the TISNE hyperparameters actually play a huge role. So definitely look for the hyperparameters that work for your particular data set. And then here we're just plotting the projected two-dimensional components of the TISNE, just like we did before. And when we do that, we get something like this. So here it's clear that TISNE did a pretty good job at separating different clusters even in 2 dimensions. So now an exercise, try to do this again for the digits dataset and see if you can get a better result than PCA. All right, so welcome back from the exercise. And as we've done previously, we're basically gonna use the same code here. And the only difference is that now we're fitting it to the digits data set, and that here we're using 10 colors instead of 5. And let's run those and see what we get. It might take a little bit longer since the digits data set is obviously much bigger than a Swiss roll. All right, and as you can see, the TISNE did a much better job than PCA here. So you can see, for example, that all the zeros are distinctly here. There might be a few exceptions here and there, but it has worked pretty well in separating each digit into its own cluster. And don't worry if this looks different than what's on your screen. It's actually the case that every time you rerun a TISNE, it's going to look different since it is a stochastic method. And just to check that, and yep, so as you can see, it looks different again, but it is similarly successful. So sometimes it's really just not enough to plot things out, and you really want to just interact with the data to learn more about it. So we're going to talk now about interactive visualization, and this is going to be mainly through the Plotly library. We're also going to be using financial data from the stock market, and Panda's data reader is a useful tool to actually fetch in real time the stock market prices. And the way this really works is by calling its data reader, and then we're going to specify the ticker for the specific stock or ETF. And for this case, we're going to use SPY for the S&P 500 exchange traded fund. And then we're going to specify which data provider we want to use. And in this case, let's use Yahoo for Yahoo Finance. And then finally, it's going to want a start and end time. And we can use Python's datetime library to create start and end times in formats that this data reader likes. So here we're starting from the start of 2008 until the start of 2018. And then we can use those again here. And then finally, we're just gonna reset the index on this data frame such that the date is not the index. And this is gonna be apparent in a minute. So let's actually just go ahead and see what this data frame looks like. We have the date as a column, and then the high price of that day, the low price, the opening, the closing price, and the volume traded in that trading day. And let's just ignore the adjusted close at this point. So Plotly syntax works a little different than what we're used to. Most of the plots are actually in this graph objects module. So here we're calling a scatter plot with the date on the x-axis and then the closing price on the y-axis. And then we're feeding that data into this go to figure, which is actually gonna show us the plot on our screen. So let's see how this looks like. All right, so it should look something like this. And the cool thing is now we can actually interact with the data. We can hover to see the actual price on a specific day. And then we can click and drag to zoom into a specific period, and then double click to go back. And this can be really useful if you want to interact with the data. So this is one type of chart, and another type of really common chart in finance is a candlestick chart. So try to make a candlestick chart as an exercise for the first 90 days of this data. You can find the candlestick chart in the Go module. All right, so to solve this exercise, we're gonna go back to this cell, and let's just copy and paste that in here. We're gonna change this into a candlestick chart. And then let's look and see what candlestick actually requires and what we have. So we're still gonna have X as the trading day, but now instead of Y, we have the opening price, we have the high price, we have similarly the low price and the closing price, and those are all things we can input to the candlestick chart. So let's see, this is going to be our data frame dot open. This is going to be our data frame dot high, and similarly our data frame dot low, and finally our data frame dot close. And let's see what we get out of this. All right, so one thing I overlooked is that we want to only use the first 90 days. So let's just take the first 90 trading days. And this is going to just take a slice and just take the first 90 days. All right, so this looks better. And so this type of chart is going to allow you to see, let's take a short segment of it. So it's going to allow you to see that the market opened here. The lowest point of the market on that day was down here, and then the highest point was over here, and then it closed here. So you know that it closed higher than it opened if one of those sticks is green, and then the opposite is if one of those sticks are red. You can also just read that information when you hover on things. So double click to zoom out. All right, so what if we want to plot more than one thing and also adding some formatting to these plots? So let's go back and paste again what we have here and see what we can build upon it. So this data variable doesn't have to be a single trace. It can be more than that. So let's get another data frame, and now let's just look at Apple stock. And we can just use the data reader again. Now the ticker is going to be Apple, but everything else is going to stay the same. And now let's append that, turn data into a list and append that to that list. So again, we're going to have a scatter plot where X is the same date, but now Y is going to be the closing price for the Apple stock. All right, and finally, let's add some layout. So instead of just inputting data here, we can input both data and layout, but we have to turn that into a dictionary. So basically, the way that Plotly syntax works is that we have to define a dictionary for data and layout. All right, so what is this layout going to be? So layout is also going to be a dictionary where we can define things like title, and that's going to be, let's say, just Yahoo Finance data. And yeah, let's just have that for now and see how that looks like. So this is actually the SPY data, and this is the Apple stock data. It says trace 1 and trace 0 here because we really haven't defined which is which. So here we can add name of that scatter plot, and let's just name it SPY. And over here, we're going to name it Apple. All right, so now, as expected, this is named the SPY, and this is named the Apple. So hovering on things and zooming in and out is cool, but what else can we do with interactive visualization? So one thing we could do is we could add interactive things such as buttons. So let's see how we can do that. So let's again copy this into here. So now the only difference is that we're going to add another thing to the layout. And this is going to be called update menus because we're going to define buttons that can update our plot. And you might be getting a feeling for Plotly syntax at this point. So this is going to be a list of dictionaries, and these dictionaries are going to be, so we're going to define buttons. And again, buttons itself is going to be a list of dictionaries. And so the things that we can define for a button are things like the label of this button. So let's say we have a button for SPY. And let's say we want to update something when we press that button. So I'm going to say method is update. And let's say that when we press that button, we just want the SPY data to actually show up. We don't want to see the Apple data anymore on the screen. So the way we can do that is that we can define arguments here. And this is again going to be a list of dictionaries. And I have a mix of how I'm defining lists and dictionaries here. This is just personal preference, and you can just use either actually spelling out dict as a function, or you could use the dictionary syntax. So the way we're going to do this here is that we're going to change the visibility. So we're going to say when we press this button, we want the first trace to be visible and the second trace to not be visible. And then we can give a title to this button as well. And let's say this title is just SPY. And I see I have an extra equal sign here, so let's get rid of that. So now that we've defined the first button, let's go ahead and define two more buttons. One where it's just gonna make the Apple data visible, and one where it's gonna make both visible again. So we're basically just gonna copy this code twice. And make two more dictionaries for those two buttons. So the second dictionary is called Apple, and it's going to make this one false and the second trace true. And the order of these traces are the order you put them in the list and the data list. So let's call this Apple. Let's call this Apple plus SPY, and we're going to make both of those true. And here as well, let's label this as Apple plus, or SPY plus Apple, whatever. All right. All right, so we've defined those three buttons, and we just have to define now which button is actually active at the start. So to do this, we're going to use active, and we're just going to use active equals -1. So it's going to make none of those buttons active at the start. And finally, to make the syntax work, we're just going to turn this into a list and this into a list again. And then let's run that and see what happens. All right, so we did it. We got these three buttons. So if we press on SPY, we're just going to get the SPY data, and then the title is going to be updated to SPY. And then if we do Apple, then we're going to get the Apple data, and then again for both, we're going to get both. All right, so now as an exercise, it's a little bit hard to compare the returns on the S&P 500 and Apple stock. So can you think of a way where you can plot both of those and make the returns more comparable? All right, so a simple way to do this is let's actually just copy all of this and paste it here. And then a simple way to do this is that instead of just plotting the absolute value of the stock on the y-axis, I'm going to plot that and then divide it by the very first value here. So this is going to be divided by the closing price on the first day. And then this is going to be divided by the Apple closing price on the first day. And now it's more recognizable that the returns on Apple would be sixfold between 2008 and 2018, whereas the returns on the S&P 500 would be twofolds. All right, so we can also look at geographical data or map data using Plotly. And I guess really the map that is on most people's minds at this point are the COVID-19 maps. So let's look at one of those. So there's a link to download this data set at the top of the notebook that was provided with this tutorial. So I'm going to import it here into a pandas data frame. And then let's look at how this data actually looks like. So FIPS is a 5-digit code that maps to every county in the US. So if you give Plotly a FIPS that is 01003, it will automatically know that you're talking about Baldwin County in Alaska. And these tend to be alphabetical. And then on each of those dates, we have the data for how many confirmed COVID-19 cases. And one type of plots we can make is that we can make a plot for the confirmed cases on each county and make that an intensity plot. So here, we're not using graph objects anymore. We're using Plotly's figure factory, and we're creating a choropleth map. The FIPS value are going to be taken from these county FIPS, and then the values, let's just take April 9th, 2020 as the value here. And then if we don't do this binning, let's actually see what happens if we don't do this binning. All right, so we have an intensity map for COVID-19 confirmed cases on April 9th. And this is exactly why the binning is important. So instead of having ranges, we have a legend for every distinct number here. So to get around that, we can use this binning endpoints argument here. And so what I'm doing here is that I'm picking a bunch of colors, and those are all shades of blue, and you'll see them a bit later. But basically, I'm picking these colors, and then I'm doing a log scaling of these colors. So we have a log scaled intensity map. So let's see what we get when we run that now. So as you can see now, we have log scaled bins. So we have 9 bins. And then this is between 10 cases and 100,000 cases. These numbers come from here. So this is 10 to the 1 is 10, and 10 to the 5 is 100,000. So there are a lot more types of charts that Plotly can make for you. Also different maps that can be animated. So these are going to be out of scope for the tutorial today, but feel free to check them out at plotly.com/python. So most likely, if you're publishing plots, your goal is to make them a way to communicate information. And some choices you make with your plots can help you do that. But making a wrong choice can put you at a risk of making plots that mislead rather than communicate. And the goal of this part of the tutorial is to help you be aware of those choices and how you can make good choices. So to start, we're going to talk extensively about color because I think it's the easiest way to be accidentally misleading. And for a very long time, a color map called JET was the standard for many plotting tools, including matplotlib. And as a result, it is now used in many scientific publications and otherwise. I'm going to first show you why it's a terrible color map, and then look at how to choose more valid color maps for your particular problem. So to start, let's actually see what JET looks like. So here I'm just creating an image, a 2D image where it's going from 0 to 100 and then making 10 rows of the same thing. And then we're going to use Seaborn's heat map to visualize that and ask Seaborn to give us the JET color map. And this will just scale each square into its correct size. So just to show you what this what this image actually looks like, let's print it out, but let's just print 2 rows and see how it looks like. So it's going from 0 to 99 as a first row, and then repeating itself 10 more times. And then, so let's plot this image out. And we can see this rainbow-ish color map. And the main problems with it is that it's not perceptually uniform, and it has 2 peaks in brightness. So you can see that around here and around here, it kind of gets really bright. In between, it's less bright, and then on the edges, it's also less bright. So sometimes when you look at a heat map like this, in grayscale or something like that, or if you're just looking at it quickly, you might feel that data points here and data points here are actually more similar than, say, data points here in the middle and data points here in the dark blue. And the reason for that is that the brightness is dramatically changing into the middle and then back to less bright in the and on the other edge. So to look more into this, I'm here going to use a code snippet from Jake Vanderplas's blog that turns a colored image into the equivalent grayscale one. So let's just define this, and then let's actually look at the flights data set for this. So I'm loading this flights data set from Seaborn, and then I want to get a heat map of the number of passengers as a function of month and year. So let's see how this looks like. Let's first plot our heat map. All right, so what this plot is trying to communicate is that in summer months, there are more passengers, and then at later years, there are also more passengers. But when I first look at this, the first thing I notice is this bright streak in the middle. And that's not what you want to communicate. You don't want to communicate that there's something very special about this bright streak in the middle. You want to communicate that this plot is actually gradually changing from left to right, and also gradually changing from top to middle and bottom to middle. So let's actually just plot a grayscale version of it using the code snippet above and see how that looks like. All right, so as we noted earlier, when we plot it in grayscale, it's very obvious that this bright streak in the middle is what's most apparent in this plot. So how can we make plots that are, or choose color maps that are more suited for this? And there are basically, to answer this question, 3 main types of color maps that are more valid, let's say, when it comes to communicating information. And the first one is, as we've noted, the problem with this color map is that it's, well, at least one of the problems is that it's not perceptually uniform. And so let's see what perceptually uniform colors would look like. The new standard of color maps in matplotlib and seaborn and others is called Viridis. And plotting this out, we see something like this, which is finally communicating the right thing, which is that things are increasing and they peak in summer months of 1960. And then, this is one of the options. There are many options of perceptually uniform colors. One of them is to actually use a single color, but use all of its different shades. So let's see how this looks like in purple. So if we say we want a color map that is purples, Seaborn gives us something like this, which is again communicating the right thing. Say you don't want purple and you want like blues, it would do the same with blue. And one thing to note is that the names of these color maps are something you might have to look up, and there are 2 links at the bottom of this, mainly here, that basically go through all the available color maps that you can pick from. All right, so the second type of valid color maps are divergent color maps. So what if you do want something to peak in the middle? For example, one of the most common examples is climate data. So let's say we're talking about the weather and we want cool colors to show cold weather and then warm colors to show hot weather. So the way I got this data is by just typing into Google Pittsburgh climate, and then I put it in a dictionary defining months from January to December, and then these are the average highs and average lows. And then I put that into a pandas data frame. So let's see how this looks like. And these are the first 5 rows of this data frame. So let's go ahead and see how this looks like in Seaborn. All right, so here we're centering our color map at 0, so anything above 0, and this is in Celsius, so everything above 0 is above freezing, and this is going to be the warmer colors, and everything below 0 is the cooler colors. And as you can see, we can easily communicate that in the summer the highs are really hot, whereas in the winter the lows are pretty cold. So let's say we don't want to center this at 0, we can choose to center it at something else, and a more common choice could be to center it at the average temperature. So here we're averaging both highs and lows and then averaging those 2 averages together, so getting the mean of each column and then getting the mean of the entire data set. And let's see how this looks like. All right, so now it's centered at the average, which is around 10 degrees Celsius, and it's showing again that everything hotter than that is going to be reddish, and everything lower than that is going to be bluish. So one thing to note is that even though here this is not a perceptually uniform color map, it does have one peak in the middle, which is not something we can say about jet, since it has multiple peaks and does not uniformly change towards the center and then uniformly change back. The third valid choice of color maps is when we're dealing with categorical data, we don't really want gradual changes. We want different types of data to be colored in very different colors. So for that, we can use categorical color maps. And one example of this could be something we've already seen in the dimensionality reduction section. So I'm just reproducing that example here, where we use the paired color map, and it looks something like this. So it uses 2 shades of each color for multiple colors, and that's an example of categorical colors where each color is basically different from the next. So just as a few practical examples, so I live in Pittsburgh, and I look at the National Weather Service a lot, their plots can be really interesting and really insightful, and but sometimes they're kind of really difficult to read. So I have here a couple of those examples that I took a few screenshots, and I'm just gonna throw them on here and look at them. So first, looking at this figure, we can see that the color bar here can be a little confusing, partly because there are a lot of colors that are not used in this figure at all. And then there's purple around here and around here that is repeated on the color bar for two very different values. And then one other thing to note is that this color bar is not uniform. So we can see that here it's going from -5 to 5, that's 10, to 15, that's 10, and so on. But then we have 35 to 75, there's 40 degrees in there. And then we have 115 to 140, and then -80 to -55. And those are all not very compatible with the rest of the values. And we really don't need to go that far, since this is looking at the wind chills in the winter, and we really don't need to go to 140. So if we had a color map maybe between here and here, that would have been more reasonable. And then on some other days, we have plots that look like this, and I would say this plot is pretty much perfect in communicating that we're gonna have warmer weather and on this streak, and then cooler weather around it, and then colder around that. So this is the color bar on this one is pretty much spot on. So enough talking about color, let's talk about a couple other choices that we have to be aware of when we're making plots and publishing plots. So the next thing we're going to talk about is about the markers. So if you're trying to highlight two types of data, if you have two types of data and you're trying to highlight them, then make sure that you plot them in either different colors or different shapes. So let's look at shapes. And let's say we have two data sets. So one goes from -2.5 to 2.5. It's two-dimensional, and there's 100 points on both the x and y. And then the other one comes from a normal distribution, and it's just 5 samples. And let's see if we can pick out those 5 samples out of the 100 other samples. So first, let's see if we had 100 of those being squares and then the rest being circles, and let's see if we can actually distinguish those. So as you can see, it's really hard to distinguish them. I really cannot find those 5 data points in the sea of other 100. Maybe this is one, but otherwise it's really hard to find. So obviously changing the color could be one thing we could do, but you should also be aware of the choices in marker shapes that you're making. So if we turn this into a plus, for example, then it's going to be really easy to pick out those 5 data points, even though we're using the same color for both data sets. So I would say try to play around with the marker shapes just to make sure that your plots are communicating what you want, and in this case that those 5 data points are coming from a different data set as the rest of the data points. And then here's another example from the iris data set. So we've plotted this before, but let's look at it again. So we're plotting the 3 species of iris flowers in 3 different colors. We're plotting the petal length and petal width for all 3 of these species. And you might not even notice, but those 3 markers are actually different shapes, and they differ in their orientation. So it's important to note that if you're trying to make a distinction between those three, you should probably use three different marker shapes that look more different than those three. So basically, this is a bad example of picking three different marker shapes to highlight three different things. One exception could be that if you're actually interested in the direction of these shapes, then that might be something to take into account. So if you want Virginica to actually be pointing to the left, then this might be actually a good choice of markers. So finally, just a reminder that although we have two-dimensional screens and we have to make plots on those 2D screens, we can make choices to basically allow us to use more than two dimensions. For example, color could represent a dimension, size could represent a dimension, and particularly for numerical data, so we can have size increasing with one numerical dimension. Shape could be another dimension, and then you could also literally just make a 3D plot and view it through some angle like we did with the Swiss roll. So some final thoughts about communication is that make use of Seaborn's capability to set a color palette for an entire notebook. So we've done this with our notebook where we've chose the colorblind friendly color palette at the start of the notebook. You could also use those two links to basically know all your options and get familiar with all your options when it comes to color maps and color palettes. And then this is probably one of my favorite resources when it comes to trying to make data visualizations that are communicating the right thing. One new package that's interesting and that's worth mentioning, but is beyond the scope of this tutorial, is called Altair. And this package is trying to make visualization more intuitive by making it declarative. So do check it out and see if it's helpful for you. And that's all for communication. And that's the end of the tutorial. Thanks for watching, and I really hope to be able to see you in person at PyCon 2021. You can find various ways of contacting me on the screen. Please do get in touch if you have any questions, suggestions, or anything you'd like to discuss. Thank you.